One of the reasons to use a matrix formulation of our models is that by manipulating the matrix, we can extract a lot of interesting properties that does not even require us to simulate the dynamics of the population. We don't have the time to go into the theory, and so I'm just asking you to take it. But if you're interested to look at how it works exactly, I, for instance, recommend you to look at the book of Sarah Otto, and with an introduction of explicit descriptions of the formal properties of transition model with constant coefficients. We can take the course on theoretical ecologies by my colleague Stu Japurka, which goes into much details into all the theory that is behind it. From our point of view now, and for the simplicity for our class, we can use the transition matrix with constant coefficient to compute eigenvalues and eigenvector. The long-term population finite growth rate of increase of the population lambda is in fact represented by the dominant eigenvalues of the transition matrix. The population age or size or stage structure can be computed by deriving the normalized right eigenvector corresponding to the maximum eigenvalue. We can compute also the reproductive value, that is the expected contribution of individuals in a given stage class to present and future production. It is the left eigenvector normalized with respect to its first age stage or age class. And then we can compute the sensitivity, the contribution of each parameter of the transition matrix to lambda, and the elasticity, that is the relative contribution of each parameter of the transition matrix to lambda. And this is very important because we can understand how every single parameter, and even errors in the estimation of the single parameters, might propagate into the estimations of the finite growth rate of the population. Just a little bit of information, the sensitivity of the finite growth rate lambda of the population to a demographic parameter zeta is defined as the incremental rate of change in lambda due to incremental change in theta. And so the sensitivity of lambda with respect to theta is equal to the derivative of lambda with respect to that specific parameter. Comparison of sensitivities for various demographic parameters are complicated by issues of scale. An absolute change of 0.1 in survival rate can hardly be compared to an absolute change of 0.1 in fecundity, specifically and especially when, for instance, we consider a broadcast spawner that reproduce millions of eggs in each reproductive event. It made more sense in this case to compute the elasticity. And for the purpose of comparison, so we can describe what are the effect of proportional changes in demographic parameter. Thus, the rankings are typically based on elasticity that is defined in this way. So the elasticity of lambda with respect to the parameter theta is equal to the derivative of the logarithm of lambda over the logarithm of theta. And by taking advantage of the property of the logarithm, this is actually equal to the derivative of lambda divided by lambda divided by the derivative of theta divided by theta, which can also be represented as theta divided by lambda times the sensitivity, the derivative of lambda with respect to theta. So the sensitivity is equal to theta divided by lambda. And elasticity is the incremental rate of proportional change in lambda related to an incremental rate of proportional change in theta. This actually probably sounds super abstract, and there is nothing like running some numerical simulation to understand it. So let's see how we can leverage on the power of R to compute everything that we need. That is the finite growth rate, which is the dominant eigenvalue, the population structure, which is normalized dominant eigenvector corresponding to the dominant eigenvalues, and then with the reproductive value sensitivity analysis. Let's say that M is the transition matrix. So in R, the function to compute eigenvalues and eigenvector is the one reported here. It's very simple, okay? And then we can extract the maximum eigenvalues, which is in our report always as the first element. So we use, we store the results of the eigenvector of the eigenfunction in VU M, and then we take in VU M dollar value is the first eigenvalue and is the dominant one, and which is equal to lambda. Okay, and then we can extract the corresponding left eigenvector normalized to 1 that provide the population structure here. Okay, so we extract it and then we normalize it. So the sum of W's is equal to 1. The reproductive value of each of the H classes given by the right eigenvector, which correspond to the maximum eigenvalues of the transpose matrix, transition matrix, can be normalized with respect to the first age or size classes, for instance. So I take the eigenfunction that we defined before, but I apply to the transpose matrix in which I swap it's a square matrix, so I can swap the rows with the column, and I extract then left eigenvectors, and then I normalize with respect to the first H class to derive, in this specific case, the reproductive value. And then I can compute the sensitivity with this exoteric formula. We'll see how, what's the meaning, but just take it, it's very simple, and this provide a matrix that represents the sensitivity. And then as we have seen it, we divide this by lambda, and so we multiply sensitivity times m divided by lambda to derive the elasticity of our function. Okay, and with this, we have concluded this first part, and we're ready to transition then to the formal definition of basic demographic parameters.